The kinetic molecular theory is the simplest model for the behavior of gases. And in this theory, we're thinking about gases as being a collection of particles, those could be molecules or atoms, that are in constant motion. So here we have an illustration of a flask containing a gas, and we've got these little vapor trail things here indicating movement, and these are the little gas particles, and they just move in straight lines until they bump into something, and then they just ricochet around. So the first big idea in kinetic molecular theory is that the size of a gas particle is negligibly small. Of course, those gas molecules or atoms have volume, but compared to the volume of the gas as a whole, they are so small that they don't matter, right? Because there's so much empty space. In a sample of argon, if the argon atoms were the size of a golf ball, the closest atom would be 4 feet away. So that's quite a big distance for a little golf ball, right? Mostly empty space. So if the golf ball was a little bigger or a little smaller, would it really matter? No, it wouldn't. Another way to think of it is to say you went to the doctor for a checkup and they always want to weigh you, right? And you're like, oh, wait a minute. I have a penny in my pocket here. I need to take the penny out before you weigh me. Is that going to make any difference? No. Does the penny have mass? Sure, it has mass. But it is so small compared to the mass of your body that it doesn't matter. So that's what we're talking about here with the volume of the gas particles compared to the overall size just does not matter. The average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. And we have to use kelvins here because on a temperature scale where we have negative numbers and zero, nothing can be directly proportional. So what this means is as you raise the temperature of the gas, the average speed of the particles will increase. Now that's the average speed. Not all of the gas particles are moving at the same speed. Some of them are going to be really slow and pokey, and some of them are going to be super fast. But temperature measures the overall average kinetic energy. When those particles collide with each other or with the walls of the container, those collisions are elastic. So if you've taken physics, maybe you know what that means. Elastic means that when those two things collide, they can exchange energy, but energy is not lost in that exchange. So here was an illustration. Probably the closest everyday thing to near elastic collisions is billiard balls, pool balls on the pool table. So here we've got two balls in motion and they bump into each other and they bounce off and they're both still moving. There is some loss of energy because that is a real world thing, but there's very little. Compared to, say, two lumps of clay, even if you made them, perfectly round, beautiful lumps of clay, and you rolled them at speed to each other, are they going to bounce off of each other like the pool balls? No, they're going to go honk, and kind of that sound, honk, and they're just going to stick together as a lump, right? That's an inelastic collision. Well, what happened to the energy, the kinetic energy that those balls had? It gets dissipated as heat, which, you can try that at home. You're probably not going to be able to tell that it got hot because it's so small. But that's where the energy goes. Any questions about that? So I think of gas particles as being a little bit like the little blip in that original video game called Pong. You guys heard of that ancient relic, Pong? So you had a blip and it would bounce off things, and then you had a paddle down here. I really need to find a video for this. You had a paddle down here and you had to move your paddle so that you could bounce the blip back up. And you could keep doing that for a really long time. And if you really got lucky, you could get it just right so it would go continuously without having to move the paddle. It just kept moving and moving and moving, and it never slowed down because it's just a computer program, right? So it's hard for us to think about gas particles being able to just move and not ever slow down, because all of the real life objects we can observe with our eyes are subject to friction. Whether friction of the ground or friction of air, there's always something slowing them down. But gas particles are not moving through the air. They are the air, right? What are they moving through? They're moving through empty space. So they experience no friction. There's nothing slowing them down. They hit a wall, they bounce off. They hit another particle, they bounce off. Any questions? We can use kinetic molecular theory to explain the things we've learned earlier in this chapter. So, what is gas pressure? Well, we've got these particles in constant motion, and they're going to strike the sides of the container with a force, right? A force over an area is equal to pressure. Those forces that the gas particles exert on the container are incredibly small, because the atoms themselves are mind-bogglingly small, right? But there are a lot of them, right? And so they add up. When my kids were younger, I really enjoyed the expression, I feel like I'm being pecked to death by a duck. You know, can a duck kill you in one peck? No. But if it pecks you enough times, you know, that could add up. Or you think about a fly. A fly comes and lands on your hand when you're doing your homework, and you twitch your hand, and it's like, oh, it's annoying. But what if the fly just keeps coming back and back and back and back? You start to feel like you're going insane, right? Because lots of little things add up, right? So lots of little impacts of these teeny tiny particles add up and can add up to very significant pressure. Any questions about that? We talked about Boyle's law, how the volume of a gas is inversely proportional to its pressure. If the volume gets bigger, the pressure gets smaller, assuming that the temperature and the amount of gas is the same. So if we decrease the volume of a gas, now those same molecules are in a smaller space. They have the same temperature, so they have the same kinetic energy, they're moving at the same pace, but now they're going to run into the walls more often because the container is smaller. If they're hitting the container more often, what does that do to the pressure? Makes the pressure go up, right? Charles' law talks about how the volume of a gas is directly proportional to its absolute temperature. Here again, we're holding the amount of gas and the pressure of the gas constant. So if we increase the temperature of a gas, then the average speed of the particles is going to increase. That will cause more collisions, and because the particles are moving faster, the collisions are going to be larger. So in order for this gas to maintain a constant pressure, we have to allow the container to expand, because expanding the container will reduce the pressure. Avogadro's law, the volume of a gas is directly proportional to the number of gas molecules. Again, constant pressure, constant temperature. So if we put more gas molecules in, then more of them are going to be hitting the walls of the container. That makes sense. So if we're trying to maintain a constant pressure, we'll have to allow the container to expand to keep the pressure the same. Any questions about those? Kinetic molecular theory of gases is one of my favorites because it's so easy to visualize. Particles moving through the air, and we can visualize this. Unlike a lot of the other ones, which are just so abstract. We learned about Dalton's law of partial pressures. The total pressure of a gas mixture is the sum of all the pressures exerted by the individual gases. So the particles of a gas are negligibly small, so what kind of particle they are doesn't matter at all. Particles of different mass are going to have the same average kinetic energy. That means if their mass is different, then their speed must be different, but the average kinetic energy is the same. And so the pressure exerted by particles is going to be the same regardless of what kind of gas they are. And the total pressure is just the sum of the pressures from each of the different gases in the mixture. There's a very nice derivation in the textbook, if you're interested, that shows how kinetic molecular theory implies that PV equals nRT. So theory is a very powerful kind of scientific knowledge. This theory predicts behavior that's consistent with observations and measurements. Of course, it does break down under certain conditions. However, looking at what happens at those extreme conditions actually helps us to understand even more about gases. So this is not the ultimate theory of gases, but it is the simplest one, and it explains most gas behavior. So let's talk about that relationship between the temperature of a gas and the molecular velocity. So this is a general equation for kinetic energy. Kinetic energy is 1/2 the mass of the object times the velocity squared. So the kinetic energy of a gas molecule depends on its mass and on the average velocity. So if we have particles with different masses, the only way they can have the same kinetic energy is if their velocities are different. So lighter particles will travel faster and heavier particles will travel slower. I'm a football mom. 4 of my boys played high school football. 1 even played in college. And so I've seen a lot of football games. And this lighter, faster, bigger, slower thing reminds me of football players. So my oldest 3 actually all played running back. And they were, slim and strong and fast, right? And number 4 played on the O-line and the D-line. And he was just bigger than his brothers. He didn't run as fast, right? And if you think of like a stereotypical guy on the D-line, big guy, right? Like maybe 300 pounds. It's like running into a brick wall. But is that guy going to be able to sprint down the field very fast? No, not at all. It's the little guys that can run fast, right? So that's kind of how it is with the gas particles. The little ones are going to be moving faster and the big ones are going to be moving slower. So if that helps, great. If not, just delete. So we talk about the average kinetic energy, and so we're going to talk about the average velocity. And what we usually use is the root mean square velocity, symbolized URMS for root mean square. It's a special kind of average, but I give you permission to just think of it as an average. So the root mean square velocity, the average velocity of a collection of gases, is proportional to the square root of the temperature and the molar mass of the particles. If we have a big mass, then the velocity is going to be smaller, right? Big guys move slower on the football field. The temperature here, if we increase the temperature, the particles are going to move faster, so the velocity is going to increase. So this is a useful equation. I don't think it's worth memorizing, but you need to know how to use it. So it's the square root of 3 times r times t divided by m, and these are 2 important details here. So here we're going to use the ideal gas constant with different units, and because the units are different, the numbers are going to be different. And so we're going to use 8.314 joules per mole Kelvin. The molar mass here needs to be in kilograms per mole, not in grams per mole. And I'm not going to try to trick you with that, but it's there, and students often forget about that. So watch out for that. And yesterday, when I did the next example, I forgot I hadn't talked about this different value, and so I used the regular ideal gas constant with liter atmospheres, and then the units are a big mess. And I realized, oh, wait a minute, let's go back and fix that. So if you want to see that train wreck, you can watch Monday's video. So this is a graph showing relative numbers of molecules with a specific velocity as a function of those velocities. And so we see that as the gas particles become smaller, oxygen to nitrogen to water to helium to hydrogen, the average velocity is going to be higher. But not only is it higher, the distribution is also much broader. There's a wider range of velocities with the smaller particles. When we increase the temperature of a gas, the velocity distribution is also going to shift towards higher velocities, and it's also going to spread out just like it did for the lighter particles. Okay, so here's the question, the problem. Calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So they're only giving us one number here, 25 degrees Celsius. But it is important that they told us it was xenon. And then the question is, we want the root mean square velocity. So that's that equation we just learned about, where the root mean square velocity is equal to the square root of 3 times r times t divided by the molar mass in kilograms per mole. So we're given a temperature, 25 degrees Celsius, that we need to convert to Kelvin. And R, this is where I messed up yesterday. We need to use the other one, 8.314 joules per mole Kelvin. And then we need the molar mass in kilograms. So xenon is 131.3 grams per mole. So we need to convert that to kilograms per mole. So that's going to be 0.1313 kilograms per mole. Now we can plug these numbers into our equation. We've got 3 times 8.314 joules per mole Kelvin times the temperature divided by this molar mass and it's the square root of the whole mess. Different calculators do square roots differently. On the 36X Pro, I can press the square root button first and then type these numbers in. Other calculators, you may need to do the multiplication and division first and then take the square root. So that's the number I'm getting. So let's look at what's happening with those units. So what we've got there is in the numerator we have joules per mole times Kelvin, and then in the denominator we have kilograms per mole, and we have the square root of the whole mass. If I'm dividing by a fraction, that's the same as multiplying by the reciprocal, right? So this is equal to joules per mole Kelvin times moles per kilogram. What can we cancel out? Well, we can cancel out the kelvins and the moles. And so square root of joule per kilogram does not sound like a good velocity unit. But I put this up here because I always forget it. A joule is equal to a kilogram meter squared per second squared. So then what that is equal to, the joule is a kilogram times meters squared per second squared. And what I have left over there is 1 over kilograms, the square root of that. The kilograms cancel out. And the square root of meters squared per second squared is meters per second. So the units here are meters per second. If you understood the unit mass, awesome. If you didn't, just believe me that the units are supposed to be meters per second. Any questions? Yeah.
We were doing mole amounts. I know there's 1,000 grams or there's 1,000 kilograms of number. So why is it the number smaller per kilogram than the one it goes on?
Well, there's not 1,000 kilograms in a gram. There's 1,000 grams in a kilogram. Right?
Oh, sorry, okay.
Yeah. That is very easy to get backwards, right? And I see, you totally can, I can just convert this to kilograms in my head, just write it down. And a lot of students can do it also. The problem is that sometimes you move the decimal point in the wrong direction, right? And so that's just something to watch out for. If you write it all out, you're less likely to get it wrong. But with the 1,000 kilograms to 1 gram, you are correct. This number got smaller when it should have gotten bigger, right? But you had the relationship mixed up. But here, so a gram, we have the big number. Kilogram, we have the small number. So small unit, big number. Big unit, small number. That can help. But thank you for asking. Did you have a question?
Is it always going to be meters over seconds, or is it going to be meters squared per second?
It's meter per second. Because I
Oh,
ended
square
up
root.
with the square root.
I
Yeah.
forgot about that.
Yeah, that's
There
okay.
you go.
That's okay. Any other questions? I mean, this happens to us all the time, doesn't it? There's something right in front of our faces. My husband and I spent 15 minutes looking for his fly fishing pack, and it was hanging from the ceiling in the garage at eye level. And we looked all over the garage, and we could not find that stupid thing, right? It just happens. So, no worries. Okay, which sample of an ideal gas has the greatest pressure? Assume the mass of each particle is proportional to its size, and that all the gas samples are at the same temperature. And we can tell by looking that the volumes are the same too. Which sample is going to have the largest pressure?
Just look at this. C.
C. C is going to have the largest pressure because it has the largest number of gas particles in proportion. The pressure is proportional to the number of gas particles. Gas B has larger particles, but that doesn't affect the pressure at all. And the smaller ones compared to the larger ones, the size of the particle doesn't matter, it's how many there are. It's just the number of them. Any questions about that? Understanding this idea, this concept, is much more important in my mind than being able to calculate a root mean square velocity.